Swayam Prabha. Digital India. Educated India.
Welcome to the Building Energy System and Auditing course on NPTEL. We are in the module number 2, where we are discussing the various types of building energy systems. The past 3 lectures we have discussed about the HVAC system, the lighting system, and also some of the electrical systems, including the pumps, including the escalators and elevators. This lecture of the 4th one and the next lecture, which is the 5th of this particular module, we will be discussing about some of the passive cooling strategies and also low energy cooling strategies. So, today in this 9th lecture, we will discuss 2 things, one of the different type of low energy cooling systems and also the earth air tube. So, as and when we called some energy efficient design, always we refer to simultaneous systems. One is the passive cooling system and one is the low energy cooling system. So, what is passive cooling system? Passive cooling systems are actually based on some design philosophy, which is driven by the nature and also by some kind of a natural energy flow that is going to be adopted in our building design. And traditionally we have a lot of strategies that includes the sun path diagram, that includes the thermal mass, that includes the certain amount of the airflow, natural airflow in the building, shading devices, orientation of the building, etc. And we try to design the building such a way that we can take the maximum advantage of this nature based cooling components and elements, and that will going to reduce our indoor air temperature or the indoor humidity or indoor comfort parameters also. Then what is the low energy system, low energy cooling system? It is conventional type energy system, what we have discussed maybe in the HVAC or maybe in the other type of system. Conventional energy resources just like electricity can be used, but there will be certain component change in that particular system. Suppose, as you know, that the HVAC system is actually based on the refrigeration cycle. So, in that particular cycle there are different components, and then some of the components we change, we manipulate, or we may have some kind of modification. Based on that modification, energy requirement will be less and will get some benefit out of it. So, it is based on some kind of a modification, and in terms of the, I have written down over here, psychometric advantages. So, whatever that advantages we can discuss in the next slide. So, suppose this is the psychometric chart. So, in that chart, as we all know, that if the state of a particular air is moved in horizontal direction, so there will be either sensible heating or there may be a sensible cooling. So, this is one of the axis. So, this is definitely going to take care of lot of energy, or maybe it will be definitely used. I mean, if you want to cool it, or you probably want to heat a particular air from one state to the other, keeping the humidity ratio same, you need to do lot of energy expenditure. The other perpendicular axis is the humidification axis. So, here you see in this black color axis or black color arrow. So, from one point to the other point, up and down we may move. By moving that particular up and down, we are not going to change the dBT, dBT will remain same, but the humidity ratio is going to change. So, the relative humidity is going to increase if you go up, and by virtue of that you will be actually either you have to take some kind of a latent heat or you have to remove some kind of a latent heat. So, this removal and the implementation of the latent heat also will going to take some of the energy, because as we all know, this particular axis is your the axis of the enthalpy, energy axis or so. So, there is any change from here to here or from here to here, we will going to have some kind of the change of energy, right. So, if this is so, so there these are the two such axes, and there is another two such axis will exist, which is inclined axis. So, this is green axis, if you see, this is evaporative cooling and the chemical dehumidification axis. Here both the things are actually going simultaneously. That means, it is sensible heat change, that is increase or decrease, and also there is a change of humidity ratio. But the important thing is that this particular axis, suppose I am going to have 3 points, one the central point and one is the further end points. So, in here as it is parallel, it is perpendicular to the energy axis or the enthalpy axis, there will be almost or negligible change of the, almost no change or negligible change of the energy. So, that is the one of the psychometric advantages we can take, and we can manipulate that, and we can think for something like a passive cooling systems or maybe the low energy cooling systems or so. So, there are another two axes exist, which is heating and humidification and cooling and humidification, but that axis is also take a considerable amount of energy in that particular way. It increases the or decreases the sensible heat, it also increases or decreases the humidity ratio or the change of the RH will take place. So, let us discuss some of the types of low energy cooling system, because we will discuss 2-3 low energy cooling systems, and also we will be discuss one of the passive cooling systems in this consecutive 2 lectures. The first one is the evaporative cooling. The evaporative cooling is, as you understand, that is the green axis of the whatever we have discussed in the last slide, and by virtue of the evaporation we increase the humidity ratio, we decrease the sensible heat consumption of a particular mass of air, and that will we can feel better, but definitely that particular system can be adopted in the hot and dry climate. So, there are two type of evaporative cooling system, one is called direct and another is called indirect, we will come to that. The next one is the desiccant system. So, desiccant system is another dehumidification system, where we can dehumidification or sometimes it is humidification systems, and that we can actually have two ways. There are some kind of a solid desiccant and sometimes we can use the liquid desiccant also. We will have some graphical representation of that in the next slide. We have a radiant cooling system. So, that is another different type of cooling system, which is also very economical in sense of and come under the low energy cooling system strategies. So, that we will discuss in the next lecture. We have geothermal cooling and also we have passive downdraft evaporative cooling. Of course, the passive downdraft evaporative cooling is a one type of evaporative cooling systems also. So, we will discuss in the next the lecture passive downdraft evaporative cooling, and today we will going to discuss this geothermal cooling systems. So, now let us see the first two, desiccant and the evaporative cooling. So, first one is the direct evaporative cooling systems. We just discussed that there are two type of evaporative cooling system, one is direct and one is indirect. The working principle is that there is a pad which is a moist kind of a pad, and warm air passes through that particular pad and it become cool. Warm air and also very dry, the relatively less humidity air, and by as it is a moist, this particular pad is moist, wetted pad, it will take some amount of the moisture, some amount of vapor over from that, and it become cool because there is the latent heat loss from the warm air or so. So, which is a desert cooler, kind of a desert cooler. So, climate suitability is hot and dry, and you need a supply fan, you need a pump for water has to be regularly pumped and wet to this particular pad, and other things, water reservoir you require the wetted pad or the evaporative media. So, this is a direct. In case of the indirect systems, there are two passage of air. So, one is the horizontal direction, suppose that is the warm air and the cool air what we have discussed, and another one may be another way, that is a air stream secondary path that will actually again going to flow, and by that particular flow there will be some amount of the humidity will be imported in the warm air, and that particular humidity will be taken care of by the method of cooling. So, indirect systems is incoming outside air is cooled without raising the humidity. So, there will be some kind of the humidity control will be there, because whatever the humidity will be actually gained by this warm air will be taken care of by the secondary air stream. So, this is also going to be useful for the hot and dry climate, and almost all kind of the components are required, only one heat exchanger and some exhaust fan is extra required. So, as you see, these systems are going to use some kind of a electrical energy definitely, and but by virtue of this the pattern and the component whatever we have actually provided in this particular system, we require little bit less amount of conventional energy sources or so. Now, the next we will discuss the desiccant. So, there are two types, solid and the liquid. In the solid desiccant systems, what happened, the air is actually passes through this desiccant wheel. So, if you see this lower part of the arrow, so it is passes through this desiccant wheel, and this will actually take moisture out. This particular system is going to be fruitful in the warm and humid climate, where there are lot of humidity in the air. So, whenever I take a warm and the humid air through this desiccant wheel there are some chemical, and that chemical will take that absorb the moisture, and also it is cooled down some amount, and then finally it will passes through the thermal cooler, that is again a heat exchanger. So, finally what I am getting in my condition space is that the two level of treatment. One is it will have the humidity is less, it is taken care of by the desiccant wheel, and second one is the temperature is also less, that is taken care of by this thermal cooler. Now, this particular air will be circulated, and then it will be act as return air, and it will be passing through a thermal heater, which will again increase the heat, and then again it will be going through the desiccant wheel, where it will going to take this particular moisture in. So, the desiccant wheel is now balanced. It will be somewhere in the lower part, as you see it has actually absorbed moisture, and the upper part, the other part of the cyclic operation, it will be actually the leave, or it will this particular moisture will be transferred to the air which will be going outside, the wet air outside. So, finally it will be a hot, and some kind of the wet air will be going to outside. So, this is the system of the desiccant system. It is a dehumidification kind of a system. The next one is the liquid desiccant system. In the liquid desiccant system, this is a little bit complex. So, there is a cycle of the liquid desiccant. So, if I take a hot and humid here as this red arrows, it will go up, and there is a this particular thermal exchanger is there, and through that it will be cooled down, and the liquid desiccant actually will be from the top to bottom, it will be it will spray, and when the liquid will spray and from the bottom the air will pass through, there will be a contact, and due to that contact it will going to lose the moisture. So, a dry and cool air will be actually going to come out, and that will be the treated. So, it will be dry, so there will be less amount of humidity, and this will be also cooled. So, it can again it can be used in the warm and humid climate. In the other part of the desiccant part, where I have to again get some recovery of the liquid desiccant. So, this you see this black color arrow, the black color line and arrow is the desiccant flow, and it will be actually come in the bottom part of this particular first box or the first this container, and from there is a green color arrow that is coming out, and if you see this is going to be a heat exchanger, and again it will be go to this particular the second chamber, where it will air, the cool air will be coming and there will be a hot air come out, and from there it will be again release the moisture out, and then again it can be used for the second cycle of operation. So, you see in both the cases what happened is that the liquid desiccant or maybe the solid desiccant in the first phase it will actually absorb moisture, and in the second case the reverse kind of a technique is being adopted through the heating arrangement and also, and then it will going to lose the moisture, again it is ready for the take further moisture in. So, that is the process, and as here in this process it has used the liquid desiccant as a chemical. So, this particular process is called the liquid desiccant system. So, next let us little bit we will discuss elaborate this earth air tube concept. The earth air tube concept is a geothermal process. So, the concept is if you go little bit below the surface of the earth or our surface of our any site or any soil surface, maybe around 6 to 12 to 14 feet below, the temperature at that particular zone will remain constant throughout the year. So, and that particular constant temperature will be almost about 15 degree to 27 degree, depends upon so many things. Of course, the temperature of outside temperature, normal outside temperature is depend upon the soil and moisture content and all those other factor definitely, but it will be remain almost constant throughout the year. So, the heat transfer if I can take place in that particular zone, that means if in the time of summer, suppose if I go to the next slide, suppose this is the earth, and below the earth I have some kind of arrangement of some kind of a pipes, metal pipes, and through the metal pipes the air is circulating. Which air? Now, it is from the air which is from the ambient air from some suction points. So, I am taking in and that air is passing through that particular below surface 6 feet to 12 feet below, and it is circulating. So, as the ambient air is having maybe little bit high temperature, maybe around 35 degrees centigrade, and this below that this is 27 degrees centigrade or so, whatever is the temperature of the soil. So, definitely there is a heat exchange. So, this 35 degree air which is the outdoor air, when it is passes through and it is coming out, it may come out with maybe 31 degree or something like that. So, there is a drop between the ambient air 4 to 5 degree or maybe little bit more. So, this is the concept behind the earth air tube, and then I can actually use that particular the 31 degree or the treated air. Treated air means it is just after the earth air tube treated air. So, I have already the temperature of the outside air is the drop down by 4 to 5 degree, and then I can take it to my centralized air conditioning unit, and I can use electricity to further cool it and send back to the building also. So, my total amount of energy expenditure will be less. So, this is the temperature gradient, ambient air temperature will be definitely high, and there is a drop in the air temperature due to the cooling effect of this particular earth air or the geothermal condition, and the EAT, that is earth air tube air, will be under low temperature, and I can use that one. So, there are some inside I have to put some suction point, those are the suction points, and from there this dotted line curve, dotted lines are the schematic, the view of the the pipes that was laid in this particular the site, and from there will be some kind of a collecting point, collection manhole, and from there I will take that to the this yellow color box indicating the my centralized AC unit, and this blue color shape the rectangles and whatever, that is the my building. So, this is the suction points, this is the collection manhole. So, the air with high temperature will come in. Suppose I have just now told you, suppose it is 35 degree centigrade. This is my earth air tube. So, it is moving, and by virtue of a long distance move, by virtue of a high contact time, it will lose heat and it will be collected over here as a 31 degree centigrade or so, and it will be channelized to the centralized AC unit, and from there I may send 22 degree or whatever, that may be further below, but at least my total pressure on the centralized AC unit will be less. So, I have some photographs of, you can see those are the installation of the earth air tube. So, it should have a very long space available in your site, and definitely the length of the pipe has to be more, because you need time to take care of this kind of a heat exchange. So, it can be useful for large project like building having very large landscape area, you have a university campus, you have a big hospital, and it has also lawns and all those kind of all kind of a thing. So, those kind of a scenario you can definitely go for some kind of the earth air tube. Some people say that this is not going to be a very fruitful systems, but you have to adapt that particular systems to the typical the site or maybe the project. Every project cannot give the successful result if you employ the earth air tube. For smaller buildings, smaller projects are so no, it has to be a larger site area, campus area, something like lawn area. So, for that only you have to see that particular thing has to be well equipped or so. So, the effectiveness of the earth air tube depend upon the how much is your ground temperature, what is the depth of your the tube, what is the dia of your tube, and how the tubes are going to arrange, what is the inlet temperature, outlet temperature, thermal conductivity of the pipe is very essential. It has to be metal pipe, very quickly it should exchange the heat or so. The velocity of the air, the flow rate, because inside the air should be very slow, of course not so slow that it cannot draft a proper amount of outlet the requirement of the flow for your air conditioning purpose. So, there should be a moderate kind of a flow and definitely the system efficiency. So, here we see there is a kind of a trade off we can see between the heat exchange process. So, in the first box whatever I have written down is that the surface area of the pipe, if it is higher it will increase the heat transfer rate, and the contact time and the airflow, if it is higher definitely it will be the higher transfer. Tube material has to be very highly thermal conductive to increase the thermal or heat transfer. So, therefore, we have to optimize the tube length, so that it will give me the economy and also will give me the some kind of the efficiency of the system. Okay, so, after certain length, certain amount of the dispersion or the movement, the heat exchange rate will fall down. So, we should not go more than that length. So, we have to also see that one where this pressure drops, because then the draft will be not so proper. So, length and all these things has to be taken care of. So, efficiency of the systems will be given by this formula Ti minus To divided by Ti minus Ts, where Ti is the inlet temperature, how much is the outside air temperature through the inlet, To is the outlet temperature which is after moving through the earth air tubes, how much is the temperature of the air which is in the outlet, and Ts is the soil temperature. We also try to find out the COP. COP is the coefficient of performance of the system, where it is defined as the Q by W, where Q is your thermal benefit, how much benefit I am getting by virtue of this system, and divided by the W is the some work I have to do, some energy expenditure by fan, by some kind of a pumping system I have to provide. So, that is your W, so your whatever your expenditure, and what is your gain is your Q. So, the gain versus expenditure is a ratio, and definitely gain has to be more. otherwise why should I go for or adopt for that. So, if the Q is more than W, COP is greater than 1, it is efficient, and if it is less than 1, then it is an inefficient system. So, a small numerical problem let us solve. So, I have given the data. So, in the data I have given the room, I have stated that this room needs 6 air exchange per hour. So, I can calculate how much is the flow of the air, and I have assumed that 50% of the outdoor air is treated through the EAT and the 50% is the normal. So, the 50% of the air I will take through this the earth air tube, and I will drop down the temperature. The outdoor ambient temperature is 38 degree, quite high, and the indoor temperature I want to retain as 25 degree centigrade. So, and I have estimated that a 5 degree centigrade temperature drop will be achieved by the EAT. So, 5 degree drop means the 50% of the 38 degree air when it is passes through, I will expecting 38 minus 5, that is 33 degree will be the temperature of the EAT and soil temperature is 27 degree, and the specific heat volume and pipe diameter everything is given. The last line whatever I have written is that to operate this system I need 2 fans of 140 watt each and 1 pump of 1000 watt. So, I have to find out the coefficient of performance, velocity of the pipe of the tube of the air in the tube inside the tube, efficiency of the EAT system, and the daily savings in of the energy. So, this is the flow. So, that we have now know how to find out that one by the 6 air exchange or so, and the flow rate is also 1.25 meter cube, which is through the EAT because half of the air is from the EAT. So, by virtue of this heat loss equation, so this equation if you see, this is first one is the V into A, which is your velocity, which is your meter per second into the area of the pipe is meter square. So, finally, it is giving you meter cube per second, which is your flow rate. So, I have mentioned in the last part that it is nothing but this Q is the flow rate in meter cube per second, and SV is your the specific heat which is mentioned, and this Ti minus To is the temperature difference. So, heat loss is calculated. This is the flow rate Q, this is the SV, and this is the temperature delta T. I have told you because of this particular process 5 degree of the temperature loss is being found out, and work done by the system is there are 2 pumps of 140 and 1 I think 2 fans of 140 and 1 pump per 1000. So, this much is the that much work I am going to work expenditure, my work expenditure due to the work, and so the coefficient of performance is 6.1, which is very good. I mean more than 1 and very good number. So, 6.1 is the my coefficient of performance. Similarly, I have found out the cross sectional area, I can find out the velocity of the air, I know the Q, I know the area. So, I can find out the velocity of the air, and I can also find out the efficiency of the system because I know everything. I know the outdoor temperature, inlet temperature is 38 and your outlet temperature is there is a 5 degree drop. So, 33 degree and 27 is the soil temperature. So, efficiency of the system is 0.45. Similarly, now I can find out that how much is the energy required or so. So, through the EAT system I can find out that the first one whatever I found out that if there is no EAT system. So, only all the 100% air is actually treated to your air conditioning unit. So, your total flow rate is 2.5, that is your Q, this is your SV, and this is your delta T 13 degree, because why 13 degree, it is 38 degree to your 25 degree. So, that is your 13 degree temperature drop if you do not have any kind of EAT system. So, this is 325 kilowatt hour is your the total energy demand for 8 hours of operation. But if you are using a EAT system, then the 50% of the Q, that is the flow, will have 13 degree drop, and another 50% of the, this is 50% of overall, this is 50% of overall is a 8 degree drop. Because why 8 degree? Because this EAT temperature is down now 33 degree and your set point temperature is 25. So, there is a 8 degree drop. So, it is working for 8 hours. So, you have to actually your expenditure will be around 262.5 kilowatt hour. So, what is your total benefit? What is the total benefit for this 8 hours of operation? I have deduct 325 minus 262.5, and also I deduct 1.28 into 8, because this 1.12 is your nothing but your this much, this is your work done. So, that also has to be taken into account. So, so finally, your total amount of benefit out of this system is 52.26 kilowatt hour, which is very good. So, that is why it is called as a low energy cooling systems. You are getting the same effect, 25-degree temperature, but a portion, a part of the air is treated through the earth air tube. You are dropping down the temperature by 5 degree. That means you are using some kind of energy for running the fan and the pump, but still you are having 52.26 kilowatt hour of benefit. So, this example will show that a earth air tube is beneficial, but of course, this is having some of its own disadvantages. I have already discussed that one, and that disadvantages are that you have to be very careful about choosing the particular project. So, low energy cooling systems operate in few components, alternating of the few components of the conventional systems to reduce the energy consumptions or so. Earth air tube is one of that. Thank you very much.